This is the 29th video in a series that I'm making to support a course in elementary number theory. And in the last video, we looked at integer partitions, the basic examples, and Farrer's diagrams. And now we're going to look at one of the most powerful tools for studying integer partitions, and that is generating functions. So this topic is not typically done in an elementary number theory class, but I think it fits in really nicely. Okay, so let's look at a first definition. So let's say we've got a sequence of numbers, and now we're not requiring these numbers to be natural numbers or integers or rational numbers or even real numbers. They could be complex numbers. A0, A1, A2 up to AN. The generating function for this sequence is given by the following expression. So I'll call this capital A of Q. So Q is like a variable. And then we've got A0 plus A1Q plus A2Q squared plus A3Q cubed, and then so on and so forth. So how we're encoding this sequence into a function is that it's a power series where the coefficient of Q to the n is the nth term of this sequence. And so that's what we've got down here. We've got the sum as n goes from 0 to infinity of a sub n Q to the n. And we're going to take the approach that Q is a formal variable. So it's really just like a placeholding term. And this is like a combinatorics type approach. Although you could take the approach that Q is equal to e to the I 2 pi tau, where tau comes from the upper half plane in the complex numbers. And this is generally the approach taken in the study of modular forms and stuff like that. Okay, so let's look at a couple of basic examples. So maybe the first example, which is actually one of the most important, is what if we've got the constant sequence 1? So in other words, A0 is A1 is A2 is A3. They're all equal just to the number 1. So we can encode that as AN equals 1 for all n in non-negative integers. Okay, so in this case, our generating function is pretty easy to write down as a series, but we'll want to take advantage of some stuff from calculus to write it in a more compact notation. So this is 1 plus Q squared plus Q cubed plus Q to the 4th, but that never ends. And then we would also maybe write this as the sum as n goes from 0 up to infinity of Q to the n. And that is the generating function by the definition. But like I said, we want to use some tools from calculus to write this in a more compact form. And so we'll notice that if we were thinking of Q as a real variable or even a complex variable, then this would have some sort of interval or radius of convergence. And we could talk about writing this as a rational function. And in fact, in this case, this is just a typical geometric series, and this would sum to 1 over 1 minus Q. And in the study of generating functions, and as we'll see in partitions, this series is actually very important. The fact that 1 plus Q squared plus Q cubed and so on and so forth sums to 1 over 1 minus Q is actually a really helpful way of encoding all of this information in a really small package. So I can't stress enough how important it is to remember this geometric series summing formula right here, because we'll often write terms like this 1 over 1 minus Q when we really mean the expansion of this big power series. Okay, so now let's look at our second example. So we've got A0 is 1, A2 is 1, A4 is 1, all of the even terms are 1, and then all of the odd terms are 0. So here my AQ is 1 plus Q squared plus Q to the 4th plus Q to the 6th, and so on and so forth. So that's still a geometric series. My starting term is the same, but my common ratio is different. Notice my common ratio is now Q squared. So I can sum this up to 1 over 1 minus Q squared. So when we're doing like some calculations involving generating functions, it's easier to work with this rational function than it is to work with this big series. but we're always thinking about this big series as happening under the hood. Okay, so now let's look at this last example. Well, the last example on this board, and that would be all of the even terms are 0 and all of the odd terms are 1. So this is really related to our previous example. So here we have a of q is q plus q cubed plus q to the 5th plus q to the 7th plus ... Again, that's a geometric series. Now our starting term is q and our common ratio is q squared. So by calculus 2, we know what that sums up to as well. That sums up to q over 1 minus q squared. So that's what we would write as the generating function for this sequence. Okay, and then just as a reminder, what's the standard formula for the sum of a geometric series? Well, it goes like this. We've got the sum as n goes from 0 up to infinity of a times r to the n is a over 1 minus r. And this is good when the absolute value of r is less than 1. Again, we're taking q to be a formal variable, so we don't really need to worry about this. But this is nice to keep in mind. So often we say a is our starting term and r is our common ratio. Okay, let's clean this up and then we'll look at another example. Now we've got a little more complicated of an example. And so this will be good for practice, recalling some of the stuff from calculus that's really useful when working with generating functions. So we've got our sequence a sub n, which is n plus 1 times 2 to the n. So I've written out the first couple terms. So 1, 4, 12, 32, 80, then so on and so forth. But we've got the closed form, so it's easy to calculate the terms. So really, we're just practicing building a generating function here. Okay, so let's do our generating function. So we've got a of q is equal to the sum as n goes from 0 up to infinity of n plus 1 times 2 to the n times q to the n. Because we've got our nth term times the nth power of q. Now we'd like to sum that into some sort of rational function, so we've got a nice compact form to deal with. How can we do that? Well, notice we've got this n plus 1 in front of all of this stuff to the nth power. So to me, that looks like we've taken a derivative. So let's maybe flesh that out a little bit. So this is going to be equal to the sum as n goes from 0 to infinity of n plus 1 times x to the n, where we've evaluated this at x equal 2 times q. But look at this. This looks like exactly the derivative of x to the n plus 1. So let's write that here. This is the derivative of x to the n plus 1. N plus 1 comes down, and then we reduce the exponent by 1. So that means we could rewrite this as the derivative with respect to x of the sum as n goes from 0 up to infinity of x to the n plus 1. Great. And then after that, we're evaluating this at x equals 2 times q. But look at this. This is a geometric series again. But the starting term is not 0 because of how the indexing works. Let's write out the first couple of terms of this just to get an idea for what's going on here. It's x plus x squared plus x cubed plus x to the 4th plus ... So notice our starting term is x and our common ratio is also x. And we could really see that if we rewrote this as x times x to the n and then use the thing that I think we wrote in yellow on the last board. Okay, but using this geometric series summing formula, we see that we have of x over 1 minus x evaluated at x equals 2 times q. Again, because of our starting term and our common ratio. Taking that derivative is pretty easy using the quotient rule or using kind of any other trick that you want, would be to write this x as x minus 1 plus 1, and then split that into two fractions. One where you just get a constant, so the derivative is 0, and then you're just taking the derivative of 1 over 1 minus x. But generally, if you're taking this sort of number theory class, you've taken all the calculus classes, so this shouldn't be a hard time here. Okay, so that is going to give us 1 over 1 minus x quantity squared evaluated at x equals 2q. In other words, we'll have 1 over 1 minus 2q quantity squared. And if we wanted to, we could multiply that out to get a closed form, which is expanded a little bit, but I think we can just leave it like that. So we found a generating function for this sequence. Okay, now we're going to do 2 more examples, and these will involve recursively defined sequences. So our next example is a recursive sequence with 1 level of recursion. So we'll define our first term, a0, to be 1. And then for all n bigger than or equal to 0, we'll define a sub n plus 1 to be equal to 4 plus 5 times an. So I've calculated the first couple of terms here. So we've got 1, 9, 49, 249, and then so on and so forth. So from this, and maybe calculating 1 or 2 more terms, you could maybe come up with a closed form just by guess and check and then proving it with induction. But here, since our whole game is to practice using generating functions, that's what we're going to do. Okay, so we'll first find a generating function for this sequence, and then use that generating function to find a closed form for this sequence. So we'll first start with just our generating function, a sub a of q, which is the sum as n goes from 0 up to infinity of an q to the n. Now we'll pull out the first term, because that's our seed which is given, and then leave all of the rest of the terms that use the recursion to be defined. So here we've got, this is going to be 1 plus my sum as n goes from 1 up to infinity of a sub n q to the n. I pulled out the a0 term, but the a0 term is just 1 like we had discussed. But now we're going to do an index change so that we can start this at n equals 0, and that will change my n to n plus 1 in all of the indices so that we can most easily use this. So here we'll have this start at 0. That means we're going to have an n plus 1 here. That means we'll have an n plus 1 here as well. But I'm actually going to take this n plus 1 and factor one of the q's out front, just so it's a little bit easier to work with. Then next, I'm going to take this a sub n plus 1 and rewrite it as 4 plus 5a sub n using my recursive definition. So let's see what that leaves me with. I'll have 1 plus q times the sum as n goes from 0 up to infinity of 4 plus 5a sub n times q to the n. Next, I can split this guy into 2 series. So I'll have 1 plus q times the sum as n goes from 0 up to infinity of 4 times q sub n minus q times the sum as n goes from 0 up to infinity of 5a sub n q to the n. So that's what we get after all that expansion. Now we can do a little bit of simplification. Notice I could take this 4 here and factor it out, but that leaves me with something which is pretty easy to deal with right here. Notice I've got the sum as n goes from 0 to infinity of q to the n. That's exactly my geometric series. We know that sums to 1 over 1 minus q, like that. I've got the q times 4 out front, which I'll take care of on the next line. Furthermore, we see that this 5 can be factored out, so I'll squeeze that in right there. And I'm left with the sum as n goes from 0 to infinity of a sub n q to the n. But that's exactly my original generating function for my sequence. So this guy right here is exactly a of q. And I just realized this should have been a plus here. Okay, so now let's bring all that down. We've got this is equal to 1 plus 4q over 1 minus q plus 5q times a of q, like that. That's just doing all the simplification that we talked about over there. So now I have a of q is equal to all of this. I've built an equation that I can use to solve for a of q. So let's move this from the right to the left-hand side of the equation and see what that leaves us with. We'll have 1 minus 5q times a of q. That's from factoring the a of q out. equals 1 plus 4q over 1 minus q. Now we can divide both sides by 1 minus 5q, and that's going to give us a of q is equal to 1 over 1 minus 5q plus 4q over 1 minus q times 1 minus 5q. So we've got our generating function for our sequence. So let's maybe bring that up here, and then we'll use this to get a closed form. On the last board, we determined that the generating function for this recursively defined sequence could be written as the following rational function. We've got 1 over 1 minus 5q, 4q over 1 minus q times 1 minus 5q. Now we want to take this guy right here and use partial fraction decomposition to pull it into pieces. Notice this one here is already in the form that we could re-expand it as a geometric series. We can't do this with the one that's in yellow box though, but after a partial fraction decomposition, we could. Okay, so just to reiterate, we want to write this as maybe b over 1 minus q plus c over 1 minus 5q. And that's just happening to this thing in the yellow box. So how would we do that? Maybe multiply both sides of this would-be equation by the denominator. So let's see what that's going to leave us with. We'll have 4q on the left-hand side, and on the right-hand side, we'll have b times 1 minus 5q plus c times 1 minus q, like that. And now, since these two linear polynomials have different roots, we can just plug the roots in for q to quickly find b and c. So notice if we set q equal to 1, this turns into the following equation. We'll have 4 equals negative 4 times b. Notice that this like c term cancels and we're just left with this. So that's pretty cool. That tells us that b is equal to negative 1. Now we can hang on to that for just a second. And then we can do a similar calculation or maybe just compare coefficients with what's left over. And we'll see that c must be equal to 1. So I'll let you check those two details. Okay, but now plugging this up here and then combining it with what we have gives us the following new closed form for our generating function. So this is 2 over 1 minus 5 times q minus 1 over 1 minus q. So now we'll re-expand those using geometric series. So this is 2 times the sum as n goes from 0 to infinity of 5 to the n times q to the n, and then minus the sum as n goes from 0 to infinity of q to the n. Again, that's just because those are standard formulas for geometric series. We can put all this together and we see that we have the sum as n goes from 0 to infinity of 2 times 5 to the n minus 1 times q to the n. But now keeping in mind that a of q is really defined to be the sum as n goes from 0 to infinity of a sub n q to the n, we can see that this a sub n has the closed form, which is given by that blue box. In other words, it is 2 times 5 to the n minus 1. So putting this all together, we have found a nice closed formula for our recursively defined sequence. So let's maybe sketch one more example of this type of calculation. For our last example, we're going to look at the Fibonacci numbers. So let's recall that those are defined by these two seeds. F0 is 0, F1 is 1, and then Fn plus 2 is equal to Fn plus 1 plus Fn. One term is equal to the sum of the previous two terms, and that's for all n bigger than or equal to 0. Okay, so let's get to this. So our generating function, I'll call it f of q. That'll be this sum as n goes from 0 up to infinity of f sub n q to the n. Since we have two seeds, we want to pull those two seeds out. But notice the first seed is 0, so that's not going to show up. That's our constant term. Our second seed is 1. That's attached to q to the first power. So I've got 0 plus q to the first power times 1. I'll leave the 0 in there just as a reminder for now, but obviously we'll not carry that all the way down. And next, we'll have this sum as n goes from 0 up to infinity of fn q to the n. And sorry, that n should have started at 2 because we took the first 2 terms out. Now I'll re-index this sum just like we had done before. So it now starts at 0, and it has an n plus 2 here and an n plus 2 here. Then we'll take 2 copies of this q and pull it out front so that we have a q squared. And then to that fn plus 2, we'll apply our recursion. So let's see, that's going to leave us with q plus the sum as n goes from 0 to infinity. We have a q squared in front of that sum. And then fn plus 1 plus fn times q to the n, because I just applied my recursion. Now we're going to split this into pieces. So I've got q plus q squared times the sum as n goes from 0 up to infinity of fn plus 1 times q to the n, and then plus q squared times the sum as n goes from 0 up to infinity of fn q to the n. Again, that's just from distributing this kind of stuff around. Well, notice that this guy right here is in good shape already. That looks like our original definition for our generating function for these Fibonacci numbers. So I can just replace this with f of q. I can't quite do that here though. That's because the index does not match with our exponent of n. But now we're going to do a couple of tricky moves in a row. So first I'll re-index this so it starts at 1 instead of 0. So that means I can start this at 1. But that's going to change this f sub n plus 1 to just f sub n. That'll change this q to the n to q to the n minus 1. Next, I'll take this q squared, split it up into q times q, bring one of them inside to cancel that minus 1 out because I've multiplied one of the q's in. Then I'll change my index again from 1 to 0 by adding the 0th term in. But we're in luck, the 0th term is 0, so I can add that in without doing anything at all. So now I'm left with the sum as n goes from 0 to infinity of fn q to the n. And the only change that happened in the end was this q squared became a q to the first power. But let's notice that this guy right here is now another copy of this. So let's see what we can do. We've got this is equal to q plus q times f of q plus q squared times f of q. But now we can move some things around. Notice we can maybe move all of this to the other side of the equation and then solve for f of q. So that'll give us f of q equals q over 1 minus q squared, like that. And then how would you find a closed form of this? Well, you would want to factor that denominator. But factoring this denominator is not going to involve rational numbers. It will involve irrational numbers. And then split it up using partial fractions. So maybe I'll leave that as one of the warm-up exercises, is to split this up with partial fractions and find a closed form. So now maybe we'll clean up the board and I'll give you guys a couple extra warm-up problems. Here are a couple of nice warm-up problems. So the first is to find the generating function for the following sequence. So 1, 2, 3, 1, 2, 3, 1, 2, 3, and then repeating forever and ever and ever. So this is the 0th term. This is A0, A1, A2, A3, A4, A5, A6, and then so on and so forth. Okay, next, let's set A0 equal to 3 and an plus 1 equal to n plus 1 plus 3 times an. So this is a recursively defined sequence with a one-step recursion. So you'll have 2 tasks here. First is to find the generating function, and second is to use it to find the closed form of this sequence. And that's a good place to stop.